So this is the third part of the paper entitled A Public Platform for Virtual IoT-Based Monitoring and Tracking of COVID-19. Authors are Jun Chanchu and Ronel Agurto. So the fourth part will discuss SDNC-centric tracking and real-time information services. So basically, the paper will propose a platform which use a centralized approach based on the software-defined network controller. However, from the CDC perspective, it is a decentralized method. So basically, this section will first offers a way of how we will link the SADB setting between our CDC and SDNC. At the same time, it will show how the centralized SDNC collects information from distributed information providers around the world. In addition, this chapter will propose a way to receive information from the information consumer perspective in real time. So let's start first with associating SADBs between CDC and SDNC. This paper will use 128-bit DH key, which only means that it will give each CDC up to 2 raised to 128 combinations of keys under its management. If we consider the total number of keys for which each CDC will use a different set of global parameters for the DH key exchange, it will handle a large amount of users. If we're going to consider 128 keys, so it will range from the 2 raised to 128 keys possibilities. So basically, scalability in the space of the key can be guaranteed. If we're going to cover enough number of the worldwide CDCs, as well as a number of large people which will manage each of those CDC, let's say if a CDC control n BOIT nodes, the CDC will only needs to associate n DH key with SDNC. However, if these DH key exchanges do not happen at the same time, in addition, each DH key exchange between CDC and SDNC will not require a real-time process. If going to consider a figure, this figure, CDC and SDNC, let's say, will wish to exchange a group of keys. Here, the total number of secret keys, which is represented as n, will be equal to the number of people the CDC will need to manage. Let's say first, CDC will select random variable n integers to make what we call as the secret value table or SVT of the CDC. It is represented as SVT of D of XD of 1, XD of 2, XD of 2, XD of 3 up to XD of n. And then it will compute n corresponding blind value to make what we call as the blind value table of the CDC, wherein the blind value table of YD of 1, YD of 2, YD of 3 up to YD of n can be computed as using this particular formula, wherein YD of k is equals to a raised to XD of k mod q, wherein the I here or the variable here can be ranged from 1, 2, 3 up to n. Then the CDC will now send association requests here with the information of case A EI, case A E2 up to case N to the SDNC. While the SDNC will receive this request, the SDNC now can select n random integers to make his own secret value table. So here, SDNC will generate his own secret value table. Secret value table of x of S1, x of S2 up to xs of n. And then it will also compute n, which will correspond to its blind value table. So it will make its own blind value table also, which is represented of ys of I, ys of 2 up to ys of n, wherein it can compute blind value table as represented 2ys of k using this formula. So ax of sk mod q. After the association process is completed between the CDC and SDNC, they can now exchange their blind value table. As a result, the CDC and SDNC will maintain their own SADB, okay, or what we call as the database of their security association. Each of their entry in this paper is what we call as SA, or the security association, which is identified by the CDC blind value table. That is the field value of the BOIT node ID. So this figure will represent that particular process. So each of the BOIT node is responsible for sending an update RR message to the SDNC. Let's say, when there is any need in any change in its RR, when the SDNC receives the update RR message from a certain BOIT node, a real-time DP-Hellman key computation is necessary to compute the corresponding DH key. So if you're going to consider here another figure that we use, let's say when any change in BOIT RR occurs, the BOIT node will send the update RR message to the SDNC. This message will contain the safe part encrypted with the CDC side key of KD of I. That is EAES. Okay? So this as well as its blind value of YD of I in a clear form, so the attackers cannot decipher the update RR message. In addition, the blind value of YD of I here in that message has no relation with the person who owns the blind value. So considering receiving the update RR message, SDNC will first search the SDNC side secret value XS of I. Okay? So it is clear here that the corresponding to the blind value of YDI from the SDNC, then the SDNC can compute the DH key as using the formula KS of I is equals to Y D of I X of SI mod Q. And then it will carry out the AES decryption process of the DAES, which can be computed using this parameter. Okay? So using the SDNC side key of KS of I, this SDNC cannot actually authenticate the sender of the update RR message by checking if the decrypted value of YD of I equals to the blind value of the YD of I. Okay, so if we will check here if the decrypted value in the SDNC will be the same as the blind value of the YD of I. So now, the SDNC can update the YD of I index entry in its own RRDB. So this is how the RR can be updated in the RRDB at SDNC. So, let's now proceed with how querying RRs match with the index list. So CDC obtains the necessary RR data from RRDB at SDNC via the query reply mechanism, like the CDC or the DNS. When CDC sends the query message to the SDNC, it will use what we call as the index list. That will stands for a combined list of words such as the location information and the type of the person CDC wants to observe. So when the query message arrives in the SDNC, it will search to find RRs related to the requested index list. So how it can be performed? So let's now consider here another figure. So this figure will show the example case that query matches two RRs, index RRs, and the YD chi index RR. Let's say, if the SDNC will send these two RR to CDC as their reply message, Here, the SDNC will find the information CDC is looking for from the RRDB, and it will answer it without processing it. So there's no processing significantly, thus reduces the SDNC's computing load to handle queries and replies, and also reduces the amount of time which will spend on one-time query reply try from the CDC viewpoint. So this is really important. When the CDC will receive this reply message, first it will calculate the relevant keys, okay, KD of I, KD of K. Using these keys, the CDC can decrypt the encrypted fields in the received RR. So now, the CDC analyzed the replied information. So if we're going to consider accessing the RRDB from normal users having no security association, ordinary users do not maintain any security associations. However, they can access necessary RRs from RRDB at SDNC. Those users can send the query message to the SDNC using the index list, which will contain the location information and the type of the person he or she wants to observe. Logically, when the query message arrives at SDNC, it searches to find the RRs related to the requested index list. Here, the SDNC will reply in the same way without discriminating CDCs and ordinary users as well as the query senders. If we're going to consider again another figure, figure 6, it will show the example case that the query matches two RRs, represented as YD of M index RR and YD of K index RR. Here, the SDNC will find the information the user is looking for from the RRDB, as well as to answer it without processing at all. SDNC will send these two RRs to the user as the reply message. Receiving the RRs, the query sender will neglect the encrypted fields in the received RRs. Now, it will start to analyze the content in all the cleared areas in the RRDB. Okay, so it will clearly shows here on this particular figure how to access the RRDB from the ordinary user's perspective without any security association. Let's now proceed with the next part on the discussion. So basically, to monitor the movement situations of our target who are likely to spread COVID-19 infections in real time, it is really a prerequisite conditions to prevent the spread of COVID-19. In addition, identifying their movement for me should be done globally. It will not be limited to specific regions just like what is happening right now. So from this perspective, it is explained below or in the previous slides how the paper will meet the issues mentioned in the first part, as well as to explain the merits of the proposed public platform for COVID-19 tracking. It also suggests the need for the further research. So benefits of our proposed platform will include authentication, confidentiality, scalability, and the quality of service on the latency. So let me focus on this particular part, the quality of services or the service on the latency. So the DH algorithm will uses the computations of the what we call the modular exponentiation. That is the only reason to because of a latency problem from the viewpoints of the security management. So to generate BVT, CDC, and SDNC, each will need variable n times, which will require to compute the unit modular exponentiation. However, completing blind value table does not require real-time operations. So the computing load of this degree is not a problem at all in the latency aspect of the DH key exchange. As long as the authentication check goes completed, update RR message from the BOIT nodes are registered as new entries into the RRDB or updated as the change entry content without any processing. Therefore, even the amount of N and P increases, the SDNC side latency that will occur to process RRDB content is not a problem at all. When SDNC will receive a queries RR message, it will search the relevant RR that matches with the index list requested and acknowledge the match RRs without any process, such as encryption and decryption. So even though the amount of N by P increases, SDNC side latency that occurs to handle worldwide query reply tries is not a problem. So for CDCs and ordinary users which we will receive this reply RR message, the time it takes to complete query reply procedures can be decreased considerably because of the same reason as we mentioned. So basically, this paper built a testbed to obtain latency data that will explain how long it will take to complete the update RR procedures and compute the DH keys in a real environment. So this testbed will be shown on figure number 7. So let's consider figure number 7. So the testbed to obtain experimental data that completes the update RR procedures in a real environment. So the SDNC subnet link operates over Wi-Fi with a data rate of 72 Mbps. This update RR procedures takes time to completion of the DH key agreement between peers. So this latency will consist of the round-trip network delay and the DH key computation time. While the round-trip network delay relies on the network traffic conditions, the DH key computation time mainly depends on our DH key size. In addition, the DH key computation times varies depending on the table RR request rate, as will be shown on the tables. So there are two different conditions related to the degree of the update RR request rates here. The first condition is that the CPU will assume that the smartphone CPU power is almost free when the update request arrives. And second, the CPU conditions assumes that the smartphone CPU power is already occupied by other update RR requests by 35% when the update RR request arrives. So our testbed will run on a web applications wherein the BOIT node will send an HTTP request. This request will contain the safe part encrypted with the CDC side key of KD_I. That is represented as AES, as well as its blind value of YD_I. In a clear form, as SDNCs receives the HTTP request, it will search to the blind value of YD_I from our SADB. Then, the SDNC will compute the DH keys, MOTU, and carries out this decryption process. So another figure here will shows the experimental data that explained how long it will take for the BOIT node to complete the update RR procedures. So the measured latency here will include two main factors of the network delay and the DH key computation delay. It is clearly shown here that the latency results differs a lot, which will depend on the DH key size. So if the DH key size increases to 1024 bits, the latency reaches around 1 second for the DH key size bits. For the DH key size of, however, 3072 bits, it will approaches to 10 seconds. As shown in the lower graph, the latency variation increase as the key size become large. So considering that our virtual IoT-based monitoring platform will use the 128-bit DH key, latency requirement for the DH key agreement can be satisfied enough. For this figure, It will show the experimental data that will explain the key computation time under the CPU condition. Part 1. The DHT computation delays differs a lot, depending on the DH key size. For example, the DH key size here of 3072, that the key computation delay approaches 10 seconds, where the component of the network delay has no effect. As shown in the lower graph, here, this is the lower graph, the latency variation increases as the DH key size becomes large. Considering the DH key computation delay decreases below 100 milliseconds for the 512 bits. DH key are virtual IoT-based monitoring platform which uses the 128 bits DH key will satisfy the requirement DH key computation latency. Then on the figure 10, here, it will show how the DH key computation times differs as the update RR request rates vary. It is shown that the DH key computation latency difference between the CPU conditions of first and second becomes more considerable as the key size increases. However, the difference can be negligible for the case of the 512-bit DH key. So it can be concluded that our virtual IoT-based monitoring platform, which uses the 128-bit DH key, will satisfy the requirement keys computation latency even under the condition that the computing power of 35% is occupied with handling the message or the massive update RR request. So that will sum up this part. Thank you.